Hello friends, this video on structure of atom part 25-26 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 25. To explain all this, let's start with the quantum mechanics. So if you see, the classical mechanics is based on Newton's law of motion, 3 laws, that's all. These laws describes the motion of macroscopic objects, big objects like ball is moving, stone is falling, the planet is moving. Those things it describes perfectly fine, right? Which have generally particle-like behavior and they have very small wave-like behavior because the mass is more. But when it comes to microscopic objects like electron, atom, nucleus, it fails. It fails. The classical physics fails. This is because the classical physics ignores the dual theory. It thinks that the particle is only particle in nature, right? So in that case, it ignores the dual theory, and for subatomic particle, the wave nature also plays a dominant role. And since this part is neglected, you get invalid results. So classical mechanics, classical physics is not able to answer a lot of things in subatomic particle level. And there is a branch of science that deals especially with the microscopic objects in the dual behavior of the matter, and that branch is called quantum mechanics. Very, very interesting branch to study, and it's a huge scope. A lot of things yet to be discovered in this branch. So when this quantum mechanics, which deals with the microscopic objects, is applied to the macroscopic objects, the results are same. That means the quantum mechanics can be applied both in macroscopic and microscopic, because quantum mechanics does not ignore the wave part, which is there, which is ignored in the classical physics, right? So quantum mechanics, you can say, is a better approach to physics than classical physics, because classical physics is good to understand initially because it's easy to understand the 3 laws of motions, but in actual world you can get your answer from quantum mechanics. It is difficult, but it works everywhere. And this quantum mechanics were developed independently in 1926 by Heisenberg and Solinger. These are the 2 people who developed this quantum mechanics. Very, very powerful tool, and these people are really rock star, Heisenberg and Solinger. Now let's discuss Solinger equation. Solinger has given an equation that is E phi is equal to Hamilton phi. Correct? E psi is equal to Hamilton psi, where psi is nothing but a wave function, Hamilton is a mathematical operator, and E is the energy. And this is for the atoms whose energy does not change with time. He gave a whole new mathematics to work on this function. And the total energy of the system takes into account the kinetic energy of all the subatomic particles, attractive potential between electrons in the nuclei, and the repulsive potential among the electrons. So if you see, this is your atom, they are electrons, right? There is a repulsion between them, there is attraction between electrons in the nuclei, and there is a kinetic energy for the electrons. So all these energies taken care. And the solution of this equation gives energy and psi. And psi is a wave equation. For hydrogen, solution of psi, a wave function of hydrogen like spaces with 1 electron, are called atomic orbitals. So this guy gives atomic orbitals. We'll discuss what atomic orbital is. So the wave function this gives nothing but atomic orbitals where the probability of finding electrons is x. I mean, generally it is 995%. And the probability of finding electron point within an atom is proportional to probability of finding electron at a point within an atom is proportional to xi square at that point. And when this Solinger equation is solved for hydrogen atom, the solution gives the possible energy levels an electron can occupy and the wave function for that energy level. The wave function, you know, is nothing but the orbitals. We'll discuss about the orbitals now. And the quantum mechanical results of hydrogen predicts all aspects of hydrogen atom spectrum, including something which is not done by Bohr model, for example, G-man effect, star effect. So this guy, quantum model, explains everything about hydrogen. When the Solinger equation is applied for multi-electron, right, it is a little difficult. It is a little difficult, and this cannot be solved exactly for multi-electron, but if you use some approximation method and use some computer tools, you can actually solve the Solinger equation for multi-electron also. And the main difference is the increase in nuclear charge, because of which the orbital gets contracted, and those lot of things happens, and this is a little complex equation, Solinger equation. Let's start with the quantum model. In quantum model, this is how the atom looks like. This is my nuclei, which has the protons and neutrons, and then I have electrons all around. All if you see the green, yellow, blue, red, black, they're all electrons which are there. Now it's stationary. I'll make them move just in a seconds. And then there are various orbitals, and each and every orbitals can have only 2 electrons. If you see, there is one orbital, this guy, there is 1s, then there's a big spherical again, that's called 2s orbitals, and then you have this 2p orbitals, so many 2p orbitals, and then you have 3s orbitals. I have not put electron for 3s orbitals, but generally you'll have 2 more electrons here. That's how it is. And if you see, the way it works is all these electrons, right, they move randomly. But if you observe that the black electrons always move in this p orbital, this red moves in this particular p orbitals, this blue moves particularly in this p orbitals, the yellow ones, if you see, is in this s orbital, the green one is the smaller s orbitals. So the movement of electron is random actually. You can't say that it is moving in a circular orbit or something. There is no fixed path, and this orbital which you see is something which is not concrete actually. It is just a function. Just a function which defines the probability of finding electron, right? And if you see, right, the black can occur anywhere. It's all 2 electrons. It can occur anywhere, here, 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 and that's how it is. And this p, this guy, if you see the pink one, is nothing but a p orbital. So the probability of finding electron here of these 2 electrons is high in this range, in this thing, and then we call it p orbital. The probability of finding the yellow electrons is high in this spherical space, and we call it 2s orbital. The probability of finding the green electrons is high in this spherical space. We call it 1s orbitals. And that's how it is. It's all about orbitals, and orbitals are also nothing but the wave function of Solinger equation. Correct? They're just the wave function of Solinger equation, and it's all about the probability of finding electrons. And there is no concrete path. There is nothing, as we have seen in the Bohr model, there are orbits where the electrons moves around. That's actually not the case with the actual atom. If you see the actual atom, that's not the case. It's all about the probability density. We'll learn more, but just understand this is a basic overview of quantum model where you have orbitals and the electrons just move randomly in that space, and that space is nothing but the orbitals. It's a 3-dimensional space. So there are some features of the quantum model. The energy of the electron in atom is quantized, and this is something which Bohr also told. And the existence of quantized electronic energy level is a direct result of wave-like properties of electron. Both the exact position, exact velocity of electron cannot be determined. That's what the quantum model says. And that's why the exact path of electron in an atom can never be determined accurately. And that's why we don't talk about the fixed orbits. Atomic orbital is nothing but a wave function of an electron in an atom. So there is no concrete path, there is no concrete shape that we call orbital. Orbital is nothing but a wave function. It's just a wave function that defines the probability of finding electron in the species more. That's all. So since there are many wave functions possible for an electron, so there can be many atomic orbitals for an atom. We'll discuss more of these in details. Each orbital's electron has definite energy. In any orbital, you take any orbital, the electron will have definite energy in that orbital. An orbital cannot have more than 2 electrons. Please note, one orbital, as I shown in the past picture, orbital can have only 2 electrons. In a multi-electron atom, electrons are filled in various orbitals in the order of increasing energy. We'll discuss there's a principle for that. So in multi-electron atoms, electrons are filled in various orbitals in the orders of increasing energy. All information about the electron in an atom is stored in the wave function. This is the most critical thing, wave function, and the quantum mechanics make it possible to extract this information from this function. So this wave function stores everything about the electron. The probability of finding electron at a point within an atom is proportional to the square of the wave function. Please note, this psi square is known as probability density. Is always positive because square of a number is always positive. So this guy gives the method to find the probability density of an electron. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.